And so Unit 10 Part 2 will get into destructive testing. Destructive testing is different from non-destructive testing because the test involves damage, right? Partial damage, or even complete damage or complete destruction of your specimen or test material during the test process. It is the most widely used type of material test. We break it or hammer it or just jump on it. Okay, so it also provides information that cannot be obtained through the other test, which is your non-destructive testing. So destructive tests include these things. Very first one is our familiar tensile, compression, shear, torsion, impact, hardness, fatigue, and your fracture toughness. Yeah, so you already have read all this tests in previous chapters. So let's take a look at what we're going to learn from this. Very first one is your tensile test. So in this test, the gradual increasing uni means just one, okay, axial means just one axis. So instead of 3 axes, we're using only one. So uniaxial load, so here are y axis, is applied to a test piece until that piece fails. Okay, meaning like we're gonna hit it until this piece is broken. So that means that the test piece is pulled apart until it breaks. The properties revealed from a tensile test. So what do we get from this test? We get tensile strength, okay, how much that piece can be able to stand, okay, force, and then the yield strength, your modulus of elasticity, because we're breaking it, so that's beyond its elastic limit, and then your percent elongation, and then your percent reduction, okay, in the area. Instrument, so the testing machine looks like this, and this is just one type. For a tensile test, must be able to apply a tension, meaning force, we call it load, and then measure that load and elongation of that test piece. So the sensitivity and capacity of the machine must conform to this standard. Okay, so we're following this organization ASTM, and then we're following the standard E4 for tensile strength test. So first, we're going to put a force, which is a load, applied by moving the two cross heads in opposite direction. Okay, and this movement is called the loading rate control mode. You don't have to know everything. Okay, just try to get on these tests at least one time and know generally what they are doing. And when you put it in your own words, you've got to give me all the key points, okay, what it does. And this is a very important chapter for you, so I don't even take many things out of the handout, okay? We cannot be able to skip any of it. You have to know this, because you will be the one who is going to be doing this job when you get, okay, any kind of a manufacturing job as an industrial technologist. Okay, so this movement is called loading rate control mode, and in this mode, the speed at which the tension force is applied to the test piece is going to set as a constant level. So what we're trying to do is we're putting a load on it, okay, on the specimen or your testing piece. So the load speed is adjusted, and then we're going to maintain at that level. And then the load applied on the test piece is usually measured by a mechanism built into that testing machine. So all you have to do is just load it. Okay, the machine is going to take care of all of that. Your job is to set it up. Yeah. So the elongation of the test piece is measured by an extensometer. Again, this one is going to be attached to the test bead in that instrument. So with the proper equipment, both load and elongation can be recorded. Again, you don't have to do anything. The machine is going to digitally and automatically record it for you, and then output it on a graph. Yeah, so that's pretty easy. All you have to just set up and analyze the data. So here, this is a textbook picture, a typical tensile test machine. Okay, uni-axial, and we have the load, and then the test piece is going to go into that too. So what are we calculating? We are calculating, number one, your load, which is your P. Number two, the original cross-sectional area where you put it. This 2, you're going to divide the load with that area, you're going to get your stress. Okay. Strain. First, you're going to need the length of that test piece. So your test material, you measure it, get the length right at a certain stress level. That's the original one, and that's the final one. Minus it, you get the difference, divided by the original one, and you will get the strain. Yeah. The final one is because it is a destructive test, so you will get a different length. Yeah, that's what it's saying, right? Specimen is your test piece. And we also call it a test specimen, and you can see right here, specimen, little red one, and that's what applying the load. Okay. So what we're doing is we're describing this little specimen to try to get the amount that this specimen can be able to stand. Yeah. So for a variety of specimen shapes, such as like a round, square, rectangular, can be used for tension tests, and the shape used depends on the material tested. So we have metals, round specimen, sheet plate, tube materials are called your flat specimen. Okay. Again, the machines they're different. They're different for different materials. Some of the machine can be able to set up in different different ways, okay, to accommodate different specimens. Some of the machine cannot. So the central region, here is your specimen right there. So the central region normally has a reduced cross section. So both ends are machine suitable for firm gripping because you need it, because you have to hold that specimen. And the hands of the round specimen can be plain or shouldered or threaded. Rectangular specimens are usually made with plain ends, shouldered or have a hole for pin bearing. The standard we use ASTM standard E8, and that's for the metallic material, and we use a D638 for the plastics. So when you take a look at this diagram, so here look at this, see, and that's your specimen right there. And this specimen usually has a reduced section, so that means this section right there. Here fat, here thinner, yeah? So that's called the reduced section or cross section in the central test region, with both ends suitable for gripping, meaning like we hold the specimen at both ends like that, yeah, stronger ends. And here are our distances, and we have distance between the shoulder, reduced sections right here, diameter of the reduced section, and we have a gauge length right there, and then that one is just a part of that specimen, and the overall length from here all the way to the other end. So we have different kinds of ends, shoulder one, threaded one like that, or pin for the bearing. You hold it through this pin opening, okay? Alright, splitting tension test is a little bit different from the other test. So here the test is used to measure the tensile strength. The test material is usually concrete. So you can see the big giant concrete right there. So the STM standard C496 is used only for concrete tests when you build like bridges, heavy constructions, and you have really big concrete blocks that we mold. So before you mass produce them, you have to test them. Okay, yeah. Otherwise, everything is going to fall apart and you're going to get into trouble. So this test is standard 6 inches by 12 inches cylinder, and the cylinder you will load it in compression along the diameter. Okay, narrow strips or plywood can be used as a cushioning material sometimes. Yeah? See this little wood right there? That's a cushioning material along the loading lines. It's easier than the other tests, axial tension test. Okay, so what are we measuring? Number 1, P is your load, and then L is your length, and then D is your cross-section diameter, times 2 with your P divided by your length and diameter multiplied by your pi is going to give you your tensile strength. Okay, and second, make sure you get all of the calculations. Alright, the splitting tension test uses a compression load. Yeah, that's the load, okay, to test the tensile strength of that. This is your concrete cylinder right there inside. Compression test. So here you can see the compression test setup right there. It is the opposite of your previous tension test, especially with respect to the loading direction. So instead of pulling apart a specimen, it is pressed together. And the test is, and that's why we use the name compression. So the test is used for brittle materials in applications. So what are we looking for in these brittle materials? What are we testing with it? So because we want to know the resistance to compression force is necessary, such as like building foundations and machine bases. So these materials include cast iron, mortar, concrete brick, and ceramic products. Tensile strength of these materials, they are low compared with their compression strength. Okay, see our test piece right here is being compressed. Universal testing machines, alright, you can use it for compression testing. And these machines are generally used for your lab test. There's also field equipment designed especially for compression testing. So there are many different kinds of instruments for this test. So many are used for routing compression tests of concrete specimens in the field or laboratory. Why? Is because they're less expensive than the universal testing materials. So that's why we use them. And they're also portable. So they are suitable for mobile quality control lab, right? So the quality control labs they usually go around a construction site, and sometimes the company owned, but most of the time you hire the consultants or the quality control company separately, and they go around and do these testing for them. Okay. Specimen. So in compression tests, the standard specimen for concrete are usually cylindrical, and they have like a height to diameter ratio of 2. Okay, height meaning height divided by diameter, and 2 meaning like this. Okay, so if you every time you see that, your brain got a thing like this. Okay, height 2, diameter. Okay, diameter you can do big D or small d, doesn't really matter. It's set the ratio of 2, so meaning like this. Okay, meaning like height divided by this. There's a silent 1 right there. Okay, so they are cast, right, and hardened it in an upright position. Here is the example I just showing with a tennis ball right there. They are testing the strength of that tennis ball. So the standard specimen is normally like 612 cylinder. The maximum size coarse aggregates you can't exceed 2 inches. Yeah, so you have to strictly obey the size because of the standard. Yeah, ASTM standard C and D series. Because if you exceed 2 inches, you've got to treat the sample with a different sieving, which is your wet sieving. Okay, So it's better to just stay within the standard, so you don't have to do the extra work and save time. Yeah. So both ends of your specimen should be flat to prevent stress concentration. So the end surfaces should also be perpendicular to that cylinder axis to prevent the bending due to eccentric loading. Most brittle material, they're sensitive to the loading rate. So you have to load according to your material, not so fast and not so slow. And the rate should be low for the test, okay? So recommended load rate for concrete is 1,000 pounds per minute to 2,000 pounds per minute. So that's the loading. So 1 minute you're gonna load that, and 1 minute you're gonna load that amount of concrete. Alright, so the next tests are shear and torsion tests. So we have rivets, crank pins, wooden blocks. They're all subject to shear forces. When we do shear tests, we're trying to make sure your material is for the safety and also functionality of that part. For torsion tests is a different thing. For torsion, we want to evaluate the shear properties of materials, and that's why we do this test. For shear test, we want to make sure the safety and functionality of that part, and we do the shear test. Torsion, as you know, is just a stress, right? Okay, so torsion is a specific shear stress that happens inside shaft, subject to twisting. The very first one is your direct shear, and this test is of metal, a bar, okay, here is usually sheared in a device, and that clamps part of the specimen while the remaining portion is subjected to load. You don't have to worry about everything right in here. All you have to know is this is just a test of metals, and we're testing metals by using direct shear, and we're gonna load the specimen. If you get it, that's fine. Yeah, no need to go into details. So any means of applying a load, such as like hydraulic system or a universal test machine, you can use it. What are we looking for? Your force or load required to shear that specimen. Because we're in destructive testing, we're going to shear that specimen, right? Damage it. And then we need the area of that shear plane. This time we want the area for the shear plane parallel to the loading direction. And you will divide it, and you're going to get the shear strength. Yeah. On this part, you definitely need to get it. This part, if you can remember, perfect. If you can't remember it, just for the metals, we're loading the specimen, okay? And your course require you to only do your questions in your textbook. So our line is a little bit lighter on the engineering side, so you just have to grasp the general knowledge of all of it, okay? We're in the tech field, so our responsibility is that we have to have ability to be able to use any kind of machines, any kind of applications, and you gotta just get on and do it, alright? Calculation parts and all the details are the engineer's side, okay? A little bit different because they have to do more work because they have to get the license, So it's a very different story. But then we are in the relatively same industry working together, okay? Just make sure you know where you are so you won't overstudy. Alright, direct shear. The shear plane can be either rectangular or it can also be circular. We're gonna follow ASTM B565. and that's for your direct shear test. No need to remember anything. We don't want to get it, okay, all of that. We have to just go and reference it. We call that the Johnson shear test. Your standard, so 1 by 2 inches. Your cylindrical rod, about 1 inch diameter. Specimen, you're going to first clamp it to the base. You're going to apply the force. And that force is going to rupture that specimen because we're in destructive testing. And we do only single shear, and we will break that specimen, okay? So if the specimen extended to a point and bridges the gap between the dies, it is subjected to have a double shear. Yeah? Not single shear isn't enough if you hook it up in this way. Yeah? The dies in the loading tool are made of tempered tool steel ground to an edge. For direct shear, tests of wood. Special tool and specimen, we use them. We're going to follow ASTM D143 for this test. A little bit different from the previous slide. Sometimes you're going to have failures along the shear plane. For a shear test with the glue joints, a specimen is glued along the dash line, okay? And that dash line is on the shear plane, and then you're going to load it. Again, no need to go into detail, just trying to teach you things about your instrument, okay? All you have to understand is we load, and then we break the specimen in. The specimen got to be following a particular standard, okay? So those are the things you need to know. So here you can see your specimen, a load right there, and this is your shear location right there. So for a shear test, a bar or a plate is sheared, okay? It will be sheared in a device, and that device is clamped, right? Part of the specimen, we're clamping this, you can see the clamps right there, while the remaining portion is subjected to load, and we load it right here. A little bit difficult to see, but you eventually get it if you understand the word shear, yeah? Shear is basically a cutting off something. So here you can see wood, and that's your testing specimen. And we're testing the wood and with the direct shear. Here's just the specifications right here, and you can see the specimen is right there, and you're putting your force right here, yeah? So basically we use this load to cut this off, and it is, see this little dotted line right there? That would be shear in that direction, yeah? Go all the way down, bang. Torsion is usually done in a specially designed torsion testing machine, like they're very expensive. So a driving mechanism turns a trunk that clamps onto one end of the specimen, and the trunk turns and applies torque through the test specimen. A similar chuck at the other end, so that chuck is going to measure the torque, and before a test is started, the specimen is carefully measured. So what all of that is saying is, before you start the test, you're going to measure your specimen, right? And then you're gonna set your specimen up in a machine, and those machines are usually designed, okay, especially for torsion, yeah? So what it does is gonna drive the mechanism, alright? It's gonna, here is your specimen right here, and it's all completely clamped. Here, this is your driving force right here, and that's what it's saying here, driving mechanism, right? Turns a chuck right here that clamps onto one end of that specimen, okay? And this is your driving mechanism. So the chuck turns, and then it's going to apply torque through that test specimen, right? At the other end. So this chuck is going to measure the torque. So now you have an issue. So your issue is, in order for you to understand torsion, you have to review your torque. Torque is nothing but it's just a rotational, because see this is a driving and you can see how it's rotating. It's just a rotational equivalent of your linear force. Okay, your force is linear, but then you have a rotational equivalent. So if you try to review your physics, the torque we usually draw like that, this way, like that. Okay, I'm not really good at drawing, so you have your rotation, and then you also have a force going that way, and we have a force going this way. Okay, now we have your linear is going to be your R, which is this guy right there. Your P. If you don't want to go, you can also go rotation. Okay, your torque. You have your radius, and then time. I really hate writing on this PowerPoint thing. And your force. Okay. So maybe you can remember this one from your physics. So anyways, a rotational equivalent of your linear force is your torque. This I should draw a little bit better. I should draw this one again. Rotation, so going that way. This is a little better, yeah? So anyway, you can review that in physics. So that's why you can see right here, when you take a look at this torsion instrument, you can see a rotation, your driving force, and then linear force, okay? And that's how we can be able to calculate torque. So here, torsion, your elastic range, maximum fiber stress, your torque is related to, okay, to the torque T, and by the torsion formula for circular shape. So we're gonna do the fiber stress is equal to again, don't get confused with your physics torque. Okay, that is a physics torque. It's a little bit different. Here we call this stress. So stress is related to your torque. Here we're using it with big T. So here torque times R divided by J, which is your moment. Okay, over there in physics we write moment with little p, and then your radius. Okay, and then your linear force. So here the torque in physics is now stress. The torque in physics is now T, big T. Radius remain R, the same. And then the moment in physics P is now a J. Okay, so polar moment of inertia of the cross section. So one thing very upsetting in the United States is organizations hold their own power, and states hold their own power, and the country holds their own power. So the power is so divided and distributed partially to every sectors of the country. So therefore, in science, you have a lot of confusion because they're using whatever symbols they want to do. Okay, so that's confuses so many people, because a lot of the companies in America, they do not follow standards. They buy the standards, but not truly practicing them. So people who practice science have a lot of issue with those who are not practicing science, and a lot of time goes through trying to solve all that issue. Okay, the issues are little things of confusion. And sometimes you don't understand what you're reading anymore because they're not following. So you have to start deciphering what is this company writing, some crap that I don't understand, and you can't go and say that to them either. Okay, they're just doing whatever they want. So you have to take it, and then you sit down and you try to analyze and try to understand by yourself, and then translate it back to what you normally understand. Okay, so just taking some time, you can charge some money back to them without letting them know. Okay, you can go and headbutt with them. They will never drop their pride. It's going to have issue, and you won't get your job. So if you want to do your job and you want to make money, don't go and point out the things that some people don't like. You just keep your mouth shut and then do what you gotta do, and then don't let anybody know about it. Okay, ignorance is the best. So let them do whatever they want to do, and you do what you gotta do, and work it out. Yeah, and it works that way better in many situations. So the polar moment of inertia J for solid circular bar, and we're gonna take the J out, is going to be your pi times d, right, square, and then divided by 32. So that's you. But again, nobody's going to ask you all of that except for your assignment questions from your textbook. Okay, but then it's really nice to know about this. Then we're going to follow the ASTM standard E855 for this. No need to remember anything. We are following a standard. Okay, so when you do this test, you know what to do. You have to follow a standard, so find it. They're going to give you the book or the application in your PC or whatever, and you're going to follow everything. Yeah, don't use a different standards. Strictly follow that, and it's going to make your life easier. Torsion test. Instrument, you can see it. You have your chalk applied torque right through that test specimen, because we need to set it up for linear and we need to set it up for a circular. Otherwise, you won't get your torque. So an indicator, so which is here in this instrument, is going to display the torque. Alright, the next test is your impact test. So this test is used for applications with dynamic load to test material, and we're testing toughness. So some of these applications are parts in percussion, drilling equipment, automobile engines, transmissions, body structures, tracks, buffer device, and highway guard rails. A velocity of an object is reduced as it strikes another object. Okay. So when an object is going with an energy of some sort that direction, okay, so here is your first object, and another object is going to come, let's just say this direction, and then they conflict, or they collide, or they strike. So at that time, this object traveling with initial velocity, okay, so after bumping into this little guy right here at this location, okay, after a bump, this guy, okay, is going to change into a different velocity. Okay, I shouldn't draw straight. It should go that way, this way, or whatever. Shoot out. So that's what it's telling you. Just a review for your physics. So part of whole of the first object, kinetic energy, meaning the movement, is going to transfer to the second object. That's why the velocity, okay, is going to be different. It won't be traveling with the first velocity anymore, because the KE is going to transfer partly to that guy. Yeah, and this guy KE also partly transferred to that. So therefore, the ability for that guy cannot be the same as the ability it had, right, a few moments before. So I'm going to erase this. Yeah, so some of the materials, they have like really high toughness, so that's because they absorb larger amounts of energy before fracturing. Sometimes material with very high or high roughness, they also have better resistance for impact loading. And this test is a dynamic test, alright? And what we do is we put the specimen, so this little red bar is a specimen, and we're gonna break this guy, okay, by using this load right here and impact it. So the test is gonna break this specimen, yeah. So what we do is struck, and then it's broken by this blow with a load. Okay, so the test is performed in a specially designed testing machine. It's pretty neat, by the way. So the energy absorbed in breaking the specimen, we're gonna record it. Okay. It will be recorded within the instrument, so you don't have to do anything like that. Just look at this. So that's your recorder. So this is done by measuring the difference between the pendulum heights before and after the specimen is broken. So your pendulum is things like swinging like that. Okay, that's your load, and then you're gonna hit your specimen that way. So the applied load may be flexure, tension, compression, or torsion. This guy is a compression. So flexure loading is most of the time is a commonly used method for impact test. Tensile loading is kind of less common. Okay, compressive and also tensional loads, we use it for special cases. And the most used impact tests for steel are called choppy and ease weight. Okay, so if you see impact test, choppy, impact test, ease weight, then you know that we're testing steel. The rest of them depends on whatever material that we're testing. So various kind of instruments and setup for impact test. So the most used impact tests for steel are choppy and ease weight. So both tests use the pendulum principle. It looks like that. See, here is your cartoon. So the tests are conducted on small and large specimen. Here is a little specimen right down there. To be knocked out with this pendulum load right there. We use ASTM standard E23 for choppy and ease weight. Form of material specifications or impact strength limit is established from several products like airplane, engine parts, transmission gear parts, for tractor belts, your turbine blades, your forgings, and your pipes. Choppy and ease weight testers are also used for plastics and electrical insulation materials. ASTM standard D256 is used for all these materials. Okay, so when you take a look at this here, that's your scale right there. Your pointer is right here. Your starting position, you're gonna pull it and you're gonna let go, and that's your knock hammer right there. Okay, and it's going to break this little specimen down there, right? And that's just an anvil to hold that specimen, and it's gonna move its position from here to there. Since it struck this material specimen right here, alright, the swing is going to be different from here, velocity 1 and velocity 2. Okay, here your height 1, and then here is your height 2. And here, that's your scale, and you're going to read that, yes? And here is a, in life, it looks like this. Your specimen stations right there, your anvil right here, your little pieces of specimen down there. So impact test, the pendulum is released, okay, and you have a height 1 right there. Energy is going to absorb by the specimen is measured by the difference in height before and then after height. Okay, so here coming down with the velocity, hit it. It won't go up because the energy is lost at the strike point, collision point. Okay, so the velocity is going to be slower, so the height is going to be different. Yeah, it won't be as high as that. In choppy test, this is a two-dimensional cross-section diagram. So the specimen is supported as a simple beam right here. So here we can see this specimen right here. Yeah, these are just the specification, the size of the specimen. You follow your ASTM standard, and this is your anvil holding it. And this is going to be your striking edge, because this is a destructive test, so it's going to break the specimen. That won't come down from your pendulum. So here in ease weight, the specimen is supported as a cantilever. So here, when you take a look at it, you see the specimen right here. See this one? I can a little bit difficult for you to trace the specimen. See that how you trace the specimen is right here. Yeah. Okay. I'm gonna erase this. I just trying to show you between easewide and choppy differences. So when you look at it, the first difference that you see, yeah, is a 10 by 10, 75. That's 10 by 10, 55 the size, yeah. And you have a cantilever in easewide, and this one pendulum. Right, so the next test is your hardness test, and it is defined as resistance of material to surface deformation, particularly permanent deformation, indentation, or scratching. So these tests are widely used because they're quick and easy, and some materials also can be degraded according to their hardness. So in addition, the quality of materials can be checked and controlled using hardness and tensile strength. So there are many types of hardness tests, okay? The very first one is your Bernal hardness test. So this test consists of pressing a hardened steel ball into a specimen, and we follow the ASTM standard E10, and these standards always specify the size and shape, okay? So you will have to have a 10 millimeter diameter for this standard. A load is going to be exerted, a mass of 3,000 kilograms for hard material, 1,500 kilograms for intermediate, and 100 to 500 for soft materials. So then you're going to apply that full load, about 15 seconds, to ferrous metals, and also 30 seconds for softer metals. So these are your specimens right here for testing. And then you're going to release the load, and the diameter of the indentation is measured to the nearest 0.02 millimeter using a microscope, okay? So that's how, here is your microscope right there. You can't be able to see it in the display. So if you think about the Brenner hardness test, all you have to remember is you put on a load to a specific size of your specimen, and then you pay attention to different materials, and then pay attention to how long you have applied that load, and then you look for the indentation, okay, and then measure it. That's it. Now hardness test is PHN is defined as the amount of load per unit area. So that is based on the area of indentation that remains after the load is removed. So your PHN is actually calculated by dividing this applied load by the area of the indentation on that surface. Okay, and we assume that area is spherical. That's why we're using the area for the circle right there. And of course, this is not the direct circle area, right? We have modification or adjustments right in there with it because it's not perfectly circle, it is a spherical, right? And P is your applied load, and D is the diameter of your steel ball that we use, and little d is the diameter of that surface indentation. And here we can calculate your BHN hardness number in this way. Okay. So BHN hardness number can also be calculated from the depth of that indentation, and you can use a different equation. So we have RP, your load, and then this little t right there is no time, that is the depth, right, of your indentation, and then the big D is the diameter of the ball. So this equation is compared to the other one is cleaner here. The instrument diagram from the textbook, and this guy is a digital one here. The next hardness test is your Rockwell, and it's pretty much like the other one, your Bernal test. So the hardness number is actually based on the depth of indentation, and that indentation is on your specimen. Okay, here you can see that there's no specimen on this instrument. Different loads and indenters you can use for Rockwell hardness scales, and that is depending of course on the test conditions. And these tests are widely used in industry, okay? And we follow ASTM E18 for this test. This is an instrument for a digital Rockwell hardness tester and completely connected to your computer for data. Alright, so two common Rockwell hardness scales. We use the HRB and the other one is HRC. So this one we call it Rockwell B and that one is Rockwell C. Rockwell B we're going to calculate by subtracting this from 130, so that's just adjustment. So depth of penetration in micrometer divided by 2 micrometer. Rockwell C, you're going to subtract the same from 100. Okay. So Rockwell scale is divided into 100 divisions. That's just a division on that scale, and you can see right here, yeah. And each division or point of hardness is about 2 micrometer indentation. Okay, and here. And when you think about the number, the higher the Rockwell hardness number, it means that the material you're testing is harder. Yeah, hardness is higher. So when you take a look at this instrument, you see there's a load shifter right there, and here is your hand wheel, and this is your indenter. Your specimen is going to be right on this disc, and this is your scale right here with all your divisions at 2 micrometer. So first you are going to select the scale. So for B scale is going to go from 0 to 100, so you can't use B scale if your material is harder than 100 or softer than 0. It won't work, it will go into error mode. So for Rockwell C, we can go 20 all the way to 70. So for B, 0 to 100, C, 20 to 70. And here's a table. This is just showing you the scales, the typical scales. So we have B, C, A, all the way to S and B. They're not in order, okay? But just pay attention to that. So we have a common scale, B and C, and then we have a group 2 from here to there, and then group 3 from here all the way down. And this is your indenter sizes, and then your loads. Okay, you can't go over all of these specifications. It won't work. So you have to strictly follow the specification for the Rockwell hardness scales. Next one is a Duometer hardness test. So this test is mostly used for measuring the relative hardness of soft materials like plastics and rubber. So the test method is based on the penetration of an indenter force into the material, right, under specified conditions. So this tester consists of a pressure foot, an indenter. Indenter is nothing but just this little pot right here that's going to give the force onto the specimen. And we have a display and a data port to the computer. The test is carried out by first you're going to place a specimen on this disc, okay, or flat surface. And then your indenter is going to be right here, and you apply the force, okay, and your device is going to record that impact, okay, and we will be using that translated, calculated inside of the instrument to give you your hardness number. So the pressure foot is pressed onto the specimen by using the indenter. Pressure is the same as applying the load, making sure that it is parallel to the surface of the specimen. And then the indenter is forced into the specimen, so that's your load. And then we will calculate the hardness by using that force. There are two types. We have A and then B testers. So how do we differentiate the two types? We go by the shape and dimension, okay, just like you remember that table. So type A is your Duometer for soft material, and D is used with slightly harder material, and we will follow ASTM D 2240. Here's the instrument, and that's where you're going to apply your pressure right there, or the load. So in this position, Duometer, we're using the pressure, okay? So the indenter penetration is electronically measured, connected, and you can read it out from this displays. And the value we can get out of the instrument is your hardness number, yeah? So before we get into fatigue test, you definitely need to know fatigue failure and fatigue strength. Structure, they are subjected to various varied loads, meaning like different forces. And these forces or loads is going to cause the fluctuations and applied stresses. So with dynamic loading, this is the highest stress, okay? So through maximum stress, maybe consider less than the static strength of that material. So meaning like the failure can happen if you repeat that stress, right? In dynamic loading. So fatigue failure, meaning like a failure is induced, all right, with a repeated stress, and we call that the fatigue failure. Fatigue strength is, you take a look at the stress and the stress at which the material fails, all right, by repeated force. So by fatigue, after a number of cycles, and we call that fatigue strength because that material can stand that many cycles. It's the strength of that material, okay? Now we have to know fatigue limit. So there is a stress limit for everyone, and there is a stress limit for every material. We are actually material, we're the biochemistry material, okay? Biochemical material, yes. Our stress level is, if you think about it, you have environmental stress, we have interaction stress, we have emotional stress. So every day a human is face incredible, right, amount of stress. So therefore, don't fight each other and don't yell each other. Don't, or say things that's going to make other people feel bad, because you don't want to add additional stress over the daily regular stress we all are subjected to. Okay, that's why we age every day. We become older and older every day because of that daily stress, right, on our systems. So the same thing, so all your material, there is a stress and there is a limit of that stress. Okay, the stress limit that the material can be able to stand. So we call that a stress limit in most material, below which a load can be repeatedly applied without causing a failure. Yeah. So if you apply repeatedly, again and again and again and again, the material is going to fail. It can't stand anymore. We call that the stress limit. Same as that, you can't stress yourself. So I try to tell everybody, don't stress yourself out, because if you stress yourself out, you're going to get older faster, or you're going to break down. So the limiting stress is known as endurance limit or fatigue limit, something that material can be able to tolerate. So the magnitude of the fatigue limit depends on the kind of stress variation the material is subjected to. So the purpose of most fatigue tests is to find out the fatigue strength and endurance limit of a material. Okay. We do a testing to find that limit, how much the material can be able to stand. Okay, then we're getting into fatigue tests. So there are several devices that we use, instruments that we use, equipment to do this test. They're pretty simple devices. So a typical one can apply a loading cycle in a high frequency, meaning like you can repeat the cycle again and again. And another commonly used tester or equipment is a rotating beam type. Okay, the specimen is held by one end and loaded through two bearings again, equidistant from the center of that span. So two equal loads applied on these bearings, producing a uniform bending of that specimen. Okay, but bending, you see the stress limit. So the top of the specimen is subjected to pure bending, and then the bending moment is determined by using this equation. So we've got load W, then we have, which is your little L right here, the span between the two bearings, okay, in your previous picture. And we will multiply W and L, your load and your span, divided by 2, and you will get your M. So the maximum tensile or compressive strength is your sigma, and we can calculate by getting radius. Okay, and we're going to use the bending moment, your M, and then divide it by the moment of inertia. So fatigue test, and this is your review of your mechanics. So circular specimen, we're going to calculate this way. So we have R, and you're going to find power 4 of R. So R to the power 4 times your pi divided by 4 is going to give you the moment of inertia. So fatigue limit if you want to determine the fatigue limit of that material, your specimen material, you definitely need to prepare a supply of identical specimens, of that material, representative of that material. So the first specimen is tested at a relatively very high stress. So failure can happen after a small number of stress cycle. We don't want to waste time, that's why we put it really high for the first one, and then you repeat. So all the specimens are then tested at the lower stress level. Okay, so we have identical specimen here. So first one you go high stress, and second one you go lower stress, and then the rest. So the number of repetitions required to produce failure increases as the stress decreases. Okay, so you reduce your stress, and you're going to see the repetition, the number of repetition required to produce that failure is going to increase. Okay, meaning like it takes longer if you decrease the stress. If your stress is higher, okay, the number of repetition is going to decrease. So the specimen stress below the fatigue limit it's not going to fail. So here stretch is your S versus number of cycle is N curve. We can get that graph out of the instruments if it is connected to the digital in your PC. The fatigue strength and your endurance limit, and we're going to calculate it from this graph. Okay, curve mean a graph. Remember your versus, which is your, every time you see versus, it is showing this. Yeah? We've got stretch and then on y-axis, and then we have number of cycles like that, and you have some form of a graph, and we can use this to calculate, okay, fatigue strength or stretch limit. And we will be using ASTM standard E606. We also use ASTM standard D671. So the very first one, E606, is for metals, and D671 is for your plastic specimen. Okay. From here, we can be able to get the stretch limit that this material can be able to stand. Yeah. And here you can see the typical tension fatigue tester right here. It's pretty expensive instrument, and it's definitely connected to your data collection, your computer. And here you can see the rotating beam. Where's my pointer? I always forget that. Okay. And your test specimen is right here. Your holder right here, your counter right here, your motor right here. And then this is your length, and then your width is right here. Yeah. They're just showing you this rotating, beam fatigue testing machine is going to generate a complete reverse loading cycle per one turn. The next test is your fracture toughness. So here we have already studied the hardness, the tensile, and now we're coming into the toughness. So this test is going to measure the resistance of a material to fracture. So in other words, it measures a material's ability to stop a crack from spreading. So for a thick material with a small internal crack, the fracture toughness is defined as this. So your KIC is your fracture toughness, or we just call it toughness. And that's equal to your critical stress. Okay, then you have a square root of pi, and then you have your pre-existing crack length. So that's how we calculate to get the toughness. So here is your test specimen in the loading configuration, and we call that 3-point bend, and it is testing for your toughness. So a typical specimen is, like I said before, is a 3-point bend with a loading configuration, and we always have to think about two things for specimen preparation. So what we always consider is the dimensional requirement, and your A is your pre-crack length, got to be greater than or equal to 2.5 times this. Your B is your thickness, that requirement is greater than or equal to 2.5 times this. And here the sigma Y means that's a yield strength. Okay, so you always have to pay attention for these two most important things when you prepare your specimen. But in life, in practice, alright, your KIC is not known before testing. So since we don't know this value, we have to estimate it, okay, assume it. So if the value which results from the test does not meet the requirement, the test must be invalidated. Yeah? Because we're predicting KIC. So if the value from the test doesn't meet the requirement, you just have to just throw it out. Yeah? And you're going to run a new test, and you will use a different, larger specimen. So another important consideration in specimen preparation is crack processing. So what we do is you make a little notch and you will machine that into the specimen. So here we're making a little notch like that. Yeah. And we call that the crack processing. So then a fatigue crack is allowed to develop by applying controlled loading cycles, right, in struts. So here you can see the 3-point bend right there. So a specimen with a sharp crack, right there, perpendicular to the specimen sides, you can make it. So the ratio of your pre-crack, the pre-crack is a little crack that you make, yeah. The length to the height of the specimen got to be 0.4 and 0.6. So you have your length and you have your height. That ratio got to be between 0.4 and 0.6. Yeah. So here you can see 1, 2, 3-point bend specimen, and you can use that with the regular universal test machine. Your load P is going to apply to the specimen right here, and we're doing the destructive testing, so we're breaking the specimen and we're at that point. So after you apply the maximum load to break this or fracture that specimen, and you're going to record it. The stress intensity factor, we also call that your KIC, and you will calculate that according to this formula. So KIC 3.75 times your load times your height divided by your thickness times your height, okay, and that's to the power 3/2. And this little a is just telling you this is the load on the length of that pre-crack. So you have your specimen and you have your load right here, and there's a crack right here, okay? And you have your height, which is your W right there, and there's also the height, which is your length of that pre-crack. So this is the end of part 2 for unit 10. And no need to go into details, but I do definitely recommend you to read this chapter thoroughly. So 2 chapters in the unit 10, and you definitely need to know all that testings. So all of the activities are based on all these tests, okay? And we don't just offer everything, we only offer the activity that we can be able to test, right? In our lab capacity. Sometimes we can borrow the lab from the mechanical engineering side, but then it also depends on their availability, okay? And since they have their own courses, some of the students also take it, but sometimes they don't. But then we can also do it. And I just got here, so I am developing all these labs again, because I don't know why the previous instructors did not really develop a lab for some of the classes. So, but don't worry about it, we will do it little by little, okay, to extend this program to make it better for you, so you will be thoroughly prepared for the workforce, okay? Okay, so I am going to go ahead and stop right here.